So, in the last chapter, we found that stars, like the sun and most stars, end up becoming white dwarfs, which are white hot balls of carbon. However, if you look at a periodic table, you notice that carbon is only number 6. So where do we get all of the elements heavier than carbon? Well, they're going to come from the big boys, the most massive stars of all. And even those stars have a limit. As you look at this picture here, we see that hydrogen fused into helium, and these very, very massive stars begin to look a little bit like what I like to say is a gobstopper. There's a candy, and as you suck on the candy, you go through different layers. And you have hydrogen and helium, but you can go beyond that. You can fuse helium and carbon to get oxygen and helium to get neon, and so forth and so on, up to the one right there at the core. That is nature's limit. For regular, normal fusion, iron is the stopping point. So for the low mass stars, carbon's basically the stopping point, and for the very massive stars, iron is the stopping point. We'll talk later on about how you get elements even heavier than iron, but for now, you need to know this. The longest phase by far for these massive stars is fusing hydrogen into helium. That's when they're on the main sequence. Later, they fuse helium into carbon. But every stage, the time decreases, partly just because there's less of that material to fuse, and partly because it's burning faster. So, for example, by the time you get to oxygen, oxygen is only created for 1 year. Yes, 1 Earth year inside of a star. That's it. Silicon only created for 1 week, and the amazing one, iron, the stopping point, is only created for about 1 day inside of a massive star. Pretty amazing stuff. So those elements up to iron, that's why they are not nearly as abundant as hydrogen and helium, for example. Okay, let's talk fusion for a minute. Speaking of hydrogen and helium, if you look at the left side of this curve, this is an energy curve showing how much energy you get from nuclear reactions, basically. And the left side represents fusion, where you're adding or fusing small elements together. And the right side represents fission, where you're taking big unstable atoms like uranium, an isotope of uranium, and splitting them. And the steepness of the curve represents sort of how much energy you're getting out. So you can see on the fission side, this slope is not very steep. So you're not getting nearly as much energy from fission as you do from fusion. But even on the fusion side, the big jump is from hydrogen to helium. But as the curve goes upward here, you notice that the slope is not as great. The slope is decreasing. And that's what happens in nature. The most bang for your buck is hydrogen into helium, and then helium into carbon, and it really decreases fast after that until you get to the very top of the hill right there. And that's where you have an element that you're not going to get any energy out of it naturally. Whether if you split it, if you fuse something together to create it, you're just not going to, you can't fuse it, you can't split it, you're not going to get energy from it. And that element is iron. That's why we say iron is the most stable element in nature. Okay, it won't naturally undergo fission or fusion. You can force it to, you can add energy to make it do these things, but you're not going to get anything out of it. So nature just won't naturally fuse iron, for example. That's the stopping point. Now, I would think maybe at that point, you would end up with maybe something called an iron dwarf. Maybe you'd have the same situation you had with the low mass stars, where you end up with carbon and call it a white dwarf, but that's not the way it is. Instead, the energy at this point is so great, the radiation is so intense, gamma rays flying around, that it disintegrates the core of iron that's starting to form. In just a day, in a very short amount of time, they call it photodisintegration, and the gamma rays split up the iron. Now, at that point, since there's no more fusion, iron won't fuse. That's the end of the game. Gravity wins. That ultimate battle between gravity trying to crush a star and fusion trying to blow it apart, gravity just won the ultimate battle, and the whole star collapses. Now, the really, really monster stars, of course, we know can collapse into a black hole. But nature throws up a roadblock. This is really the second roadblock that we've had. The first roadblock that created a white dwarf is when electrons repel each other and prevent the collapse. Now something new is created. Electrons and protons during this collapse are actually fused together to form neutrons. That's what a neutron is. It's an electron and a proton fused together. Kind of makes sense. You have a negative electron, a positive proton, and you end up with a neutral and heavier particle called a neutron. But anyway, neutrons themselves don't want to be pushed together. We call this neutron degeneracy. We had electron degeneracy in the last chapter that prevented the collapse of a white dwarf. Now we have neutron degeneracy, except the difference is when the electrons were pushed up against each other, you had a lot of empty space still inside the atom. Now you have no empty space whatsoever. It's neutron up against neutron. It's nucleus against nucleus. There's no empty space. It's the most dense material you can possibly imagine. It's really unimaginable how dense it is. But that dense core of neutrons can prevent the collapse into a black hole. And so the collapse actually becomes a rebound. Okay, action, reaction. It's going one direction, it hits this brick wall of neutrons and bounces off of that. Now, this is the very, very simplified version. They use supercomputers to simulate exactly what happens. So this is just kind of the high school version of this. But anyway, those are the basics. The basic way to understand it is it prevents the collapse and there's a rebound. All of this happens in less than a second. It's really hard to imagine. The collapse of a star at the very end after it's been burning for, tens of millions of years, it all comes down to this 1 second where gravity wins. But the neutron degeneracy prevents a complete collapse and there's a rebound. As you can probably imagine, this kind of scenario with the very, very massive stars, when they implode and then explode, that rebound is the explosion. This is called a Type II supernova. So, just to recap, a Type I supernova is when a white dwarf is in a binary and material pours over onto it until it eventually blows up. Very different situation here. Now you have a very massive star, a star that was born very, very heavy, and it eventually does a core collapse. It eventually collapses inward and rebounds outward. That is a Type II supernova. And any type of supernova, Type 1 or 2, the amount of energy released is just unimaginable. It can be as bright in those first few hours as the entire galaxy that it's in combined. Just imagine 200 billion stars combined. Their light is in this one exploding star. It's really unimaginable. So how do we know, how do astronomers know if it's a Type 1 or Type 2? Well, that Type 2 that just blew up looks like a gobstopper on the inside. It has lots and lots of different elements, and including hydrogen. So they look for an abundance, a spectrum that's a little more complex and more elements involved versus a Type 1. But there's one more thing that we haven't mentioned yet. If you look at the light curve, that's, remember, a graph of how bright something is over time. If you look at the light curve of the two types of supernova, there's a big, big difference. After a few hours or a few days, you see a Type 1 peaks in a matter of hours and then just slowly but surely dims over the course of a few months. But a Type 2, there's an interesting plateau. It starts to dim, but then it plateaus for maybe a few days or a few months before it finally decreases. And so astronomers look for that signature plateau to know that it's a Type 2. That plateau is actually caused by the formation of radioactive elements. Things like uranium and plutonium form at that point during that explosion. I think we get to that later, but that's what's going to cause the plateau, that extra energy involved. Okay, so what does a supernova look like from a powerful telescope? When you look at A, B, C, and D, keep in mind, these are not stars. These are entire galaxies, these little fuzzy dots on the screen. And you look at A right here. Look at A on the left. Here it is. And you have a bunch of just kind of black space here. And then over here, out of nowhere, you have a supernova. You notice it's as bright as any of these galaxies in that area. Pretty amazing. Pretty amazing stuff. Okay, so that's what it's going to look like. Just a very bright dot that appears. For example, right here, right there. That dot right there wasn't there one day. It's there the next day. That's a supernova. That's how astronomers find them. They just look for little dots that appear out of nowhere. Of course, we know they're not just little dots. Now, The most important supernova in the history of mankind occurred in 1987. Of course, the actual explosion didn't occur in 1987, but the light got here in 1987. Supernova 1987A. It was actually discovered in Chile when an astronomer in the observatory walked outside for his coffee break. So it's just ironic. He's operating one of the most powerful telescopes in the world, but he makes the discovery on his coffee break, just looking up in the sky and seeing this event happen. Why is this one the most important one? Because it's the only close supernova in modern times. Not even in our galaxy, actually. It's kind of in a suburb galaxy of ours called the Large Magellanic Cloud, but still much, much closer than any other supernova in the last 400 years. So I dare say it is the most studied supernova of all time, Supernova 19.